as we have already discussed about a specific circuit for AC supply, and there were three types of basic circuit: resistive circuit, inductive circuit, and capacitive circuit. We have discussed it separately one by one in order to make you understand well regarding the fundamentals of the circuit elements like inductor, capacitor, and resistors. And also I try to make you understand that in resistive circuit, phase difference between alternating EMF and alternating current is zero. This implies that current and voltage remains in the same phase across the resistive circuit. And after that, we have represented the variation of voltage and current with the help of their natural graph and additional graph called phasor diagram. And we have seen that in case of resistive circuit, phasor of current and phasor of voltage coincides together, indicating that the phase difference between current and voltage across resistive circuit is zero. Now come to the inductive circuit. As we have discussed that across the inductive circuit, current and voltage are not in the same phase. Current lag behind the voltage by a phase difference of pi by 2 radian, and so phasor of current and voltage in inductive circuit are perpendicular to one another, and current lags behind the voltage. That means voltage becomes maximum first, and after that current becomes maximum. Now come to the capacitive circuit. Also, in case of capacitive circuit, phase difference across the voltage, phase difference between voltage and current is pi by 2 radian. Here phase difference is positive, and hence current leads the voltage. Current leads ahead the voltage in capacitive circuit. So we have discussed all the three circuits, and now we combine all the three specific circuit together in series. So here we discuss LCR circuit, AC circuit with inductor, capacitor, and resistor connected in series with the AC source. Then such circuit is called LCR circuit. LCR circuit could be connected in parallel or in series, but here in this class you will study only series combination of inductor, capacitor, and resistors. And parallel combination is used for filter circuit, that which is not in syllabus for you. So we will focus over the series combination of inductor, capacitor, and resistor with the AC source. Now here you see an inductor of inductance L and a capacitor of capacitance C and a resistor of resistance R connected in series with a AC source which gives instantaneous voltage E0 sin omega t. Now the applied EMF appears as voltage drop across resistor as VR, across inductor as VL, and across capacitor as VC. And respectively. Now let us check out in resistive circuit. Current and voltage are in the same phase. We have discussed in the earlier section. It means phasor of current and voltage across resistive circuit coincides together. So you see here red arrow is the phasor of current representing current across the resistive circuit, and here VR is the voltage, phasor of voltage. Blue arrow is a phasor of voltage representing a voltage across the resistor. So we see here red arrow and blue arrow coincides together, indicating that current and voltage across the resistors are in the same phase. Now we discuss about inductive circuit, that is phase difference between current and voltage across inductor. In inductor, current lags behind the voltage by a phase of pi by 2. We have discussed in the earlier class. If you go back in order to understand, you see here, this is inductive circuit and it differs by a phase difference of pi by 2 and lag behind the voltage. Here phasor of current is in fourth quadrant and phasor of voltage is in first quadrant. It means current lag behind the voltage. Now, so for the case of inductive circuit, voltage VL makes an angle of 90 degree with the current, and current lags behind the voltage by a phase difference of 90 degree or pi by 2 radian. So here you see current is there, so voltage must lead the current across inductive circuit. So here you see phasor of voltage across inductive circuit is denoted by this arrow, violet arrow, and making an angle of pi by 2 radian with the phasor of current. And now for the capacitive circuit, we have seen that current leads the voltage by a phase difference of pi by 2 radian, and so phasor of voltage across the capacitor is represented by green arrow, and this voltage lag behind the current in case of capacitive circuit by a phase difference of pi by 2 radian, indicating that the voltage across inductor and voltage across capacitor forms a linear pair, and angle between the phasor of voltage across inductor and voltage across capacitor is 180 degree. Therefore, these two vectors are opposite to one another and collinear. Therefore, their differences will appear here. VL minus VC. So VL minus VC will appear as this one, will be a smaller arrow, and while VR will remain in the same position. So resultant of these two will be this arrow. You know that when two vectors are mutually perpendicular to each other, then their resultant vector can be given with the help of Pythagoras theorem. So this is the base and this is perpendicular. So this will be resultant hypotenuse. So you will see here resultant EMF equal to root under a square of voltage across resistor plus a square of voltage, effective voltage across inductor and capacitor. So this is effective voltage across LCR circuit. Now applying Ohm's law here, we will denote E equal to I into Z. Here Z is effective resistance offered by LCR circuit and is called impedance. So E equal to I into Z, because I equal to E upon Z, E is voltage and Z is effective resistance. So I equal to E upon Z. Therefore, E equal to I into Z. So if you place here I into Z here, and VR is replaced by I into R, and VL is replaced by I into XL, and VC is replaced by I into XC, where XL is the inductive reactance and XC is the capacitive reactance. So voltage is expressed in terms of product of current and resistance. As all the components connected in series, therefore same amount of current will flow across inductor, capacitor and resistor. Therefore here we write I into Z, and here I into R, I into XL, I into XC. So taking I common, and in every term I is exists in the square term, so it can be taken out of the root. So root under we will have this much things. So obviously I will get cancelled out, so you will get here Z equal to root under R square plus XL minus XC whole square. So this Z is nothing but what? Effective resistance across LCR circuit, and is called impedance. It will have same unit and dimension as that of resistance. Only difference is that impedance is a frequency dependent resistance. It will depend on frequency up to a certain range, and for the particular value of frequency, this resistance becomes independent of frequency and whole circuit will behave as a resistive circuit, and that particular frequency is called resonance frequency for the LCR circuit. Now we have learned about what is impedance. It is nothing but what? Net or effective resistance offered by LCR circuit to AC supply. That is called impedance. Why it is called impedance? Because it is a little bit different from the normal resistance that we have studied in Ohm's law, because resistance discussed in Ohm's law was independent of frequency of AC supply, but here this resistance is frequency dependent resistance. That's why its name is different from that one, but uh, behavior of this resistance and ohmic resistance is same, so it will have same dimension and same units, ohm. Now let us put here, in place of XL we place omega L, that we have already discussed in the previous section, and in place of XC we place here 1 upon omega C. So you see here, as you increase frequency, inductive reactance increases with increase in frequency and capacitive reactance decreases with increase in frequency. This implies that at a particular value of frequency, the term under this bracket becomes 0, because one is increasing and other one is decreasing. So at a particular value, the two reactance, capacitive or inductive reactance, becomes equal, and hence this term becomes equal to 0. So net effective resistance will be just equal to resistance R. In this situation, the LCR circuit behave as resistive circuit, although inductor and capacitor are present in the circuit. Still the circuit will behave as if there is no presence of inductor and capacitor in the circuit, and frequency for which LCR circuit behave as purely resistive circuit is called resonance frequency. So looking at this right angle triangle, you see here this VL minus VC is perpendicular and VR is the base. So perpendicular upon base is nothing but what? Trigonometric function tan phi, where phi is the phase difference between uh, EMF, alternating EMF and current passing through the LCR circuit. So tan phi equal to XL minus XC upon R. But one thing here left, because first of all you must start here VL minus VC divided by VR. This is one term, tan phi equal to VL minus VC divided by VR. Now we replace VL by I into XL and VC by I into XC and VR by I into R. So you will see that I taking common in numerator and denominator, and you will see that I will be cancel out each other. So we will have this expression XL minus XC divided by R. So phase difference between current and voltage depends upon inductive reactance and capacitive reactance, because R will remain constant and these two reactants are frequency dependent reactants. Sometimes inductive reactance may be greater than that of capacitive reactance, sometimes it may be smaller depending on their inductance for the given frequency. So when XL minus XC is greater than 0 or positive, then we say that phase difference between current and voltage is positive and current leads the voltage. And here we see the same expression. We have put value of XL as omega L and value of XC as 1 upon omega C. So we have expression for the phase between current and voltage is XL minus XC upon R or omega L minus 1 upon omega C upon R. But from here, this expression, we see that phase difference between current and voltage is not constant, but it is a frequency dependent. So as long as frequency is constant, then phase between current and voltage across the LCR circuit will remain constant. But when frequency is allowed to vary, then phase will also go on changing. But here we see that omega when increases, then omega L will increase, but omega 1 upon omega C will decrease. So at a particular value of frequency omega, phase difference between current and voltage becomes 0, and that frequency is called resonant frequency. And for that frequency, LCR circuit will behave as purely resistive circuit, as if there were no presence of inductor or capacitor in the circuit, although physically inductor and capacitor present in the circuit. Now we have to discuss a special case that we have already discussed there. A special case for LCR circuit when XL, that is inductive reactance, is greater than capacitive reactance, then XL minus XC will be positive and hence tan phi will be positive, so phi will be positive. And when phase difference between current and voltage is positive, indicating that current lags behind the voltage by a phase angle of phi, and LCR circuit behaves as inductive circuit, or circuit is inductance dominated circuit. Next one is that when inductive reactance is smaller than that of the capacitive reactance, then omega L is smaller than 1 upon omega C. In that case, XL minus XC will be negative, indicating that tan phi equal to negative or phi equal to negative. Hence, when indicating that phase is negative, and negative phase indicates that the current leads the EMF or voltage by a phase angle of phi, and the LCR circuit is capacitance dominated circuit or is called capacitive circuit. Now what happens when XL and XC are equal? Because at a particular frequency, capacitive reactance and inductive reactance becomes equal. For that reason, you will see that tan pi equal to XL minus XC upon R. So when XL and XC becomes equal, then XL minus XC equal to 0. And tan pi becomes equal to 0. So pi equal to 0. In this case, we see that phase difference between current and voltage is 0, indicating that current and EMF are in the same phase and the impedance does not depend on frequency of the applied EMF here in this situation. And LCR circuit behave like a purely resistive circuit, although inductor and capacitor present in the circuit. So this situation is called resonant state of LCR circuit, where impedance offered by the LCR circuit becomes just equal to resistance R, and this impedance becomes frequency independent. Now let us check out what do you mean by resonance here in AC circuit with LCR. So when XL and XC, where XL is the inductive reactance and XC is capacitive reactance, becomes equal, then omega L equal to 1 upon omega C, indicating that net impedance equal to root under R square plus omega L minus 1 upon omega C whole square. But we see here omega L minus omega L equal to 1 upon omega C. Therefore, this term will be equal to 0. So we will have only root under R square plus 0. In that case, impedance becomes minimum, and minimum value of impedance offered by LCR circuit in resonance state is just equal to resistance of the resistor connected in the LCR circuit. And in that case, when impedance becomes minimum, then current amplitude becomes maximum. That is I naught max equal to EMF divided by resistance R. EMF divided by Z, and value of Z is here R. So the impedance offered by the circuit is minimum and the current becomes maximum. And this condition of LCR circuit is called resonant condition of LCR circuit, and frequency is called resonant frequency, for which impedance becomes minimum and current becomes maximum. And LCR circuit behaves as a purely resistive circuit. So what happens at resonant angular frequency omega R, here R stands for resonant. So this subscript stands for resonance. So this frequency indicates the resonant frequency, and at this frequency capacitive reactance and inductive reactance must be equal. That is XL must be equal to XC. That is XL is given as omega R into L. Here omega R is the resonance frequency, and XC is given as 1 upon omega R into C. So omega R equal to 1 upon root under LC. That is a square root of product of inductance and capacitance. So resonant frequency can be easily calculated from given LCR circuit with the knowledge of inductance and capacitance of the inductor and capacitor present in that circuit. So this is angular frequency, and in order to obtain linear frequency, we know that 2 pi into nu equal to omega R. Therefore, nu equal to omega upon 2 pi. So we have divided this by 2 pi. So we get linear frequency. Now we have to draw a resonant curve and quality factor or Q factor. If you take, because you know that current amplitude is a frequency dependent amplitude, it is a function of frequency. So as you increase the frequency of AC supply, first current increases and becomes maximum, and after that it decreases with increase in frequency. So we will have same value of current across the LCR circuit for two different frequencies. So quality factor can be discussed here. Difference between two different frequency corresponding to which we have same value of current is called bandwidth. Here you see bandwidth equal to 2 into del omega. So let us assume that at a particular value of frequency, say, which is less than resonant frequency omega r, that might be omega r minus del omega. So this frequency will be smaller than resonant frequency. And again, another frequency greater than resonant frequency, uh, omega r plus del omega. So we have two frequency, omega r minus del omega and omega r plus del omega. But for these two frequency, we will have same current, that is I naught max divided by root 2. So this current will have frequency value omega r minus del omega and omega r plus del omega. So difference between these two frequency for which we have same amount of current called bandwidth. So here you see bandwidth omega r plus del omega minus omega r minus del omega equal to 2 into del omega. And this is nothing but what? Bandwidth. And del omega is what? Distance or frequency range from red to green, left side, and again red to right, green, right side. So now let us check out. We have so far learned about the bandwidth. Now using the concept of bandwidth and resonant frequency, we will be able to define quality factor. Quality factor, or sometimes it is also called Q factor, is defined as the ratio of resonant frequency to the bandwidth. And mathematically it is expressed as Q equal to omega r divided by 2 del omega, where 2 del omega is bandwidth. And in another way, resonant quality factor can also be defined as the ratio of potential drop across either inductor or capacitor to the corresponding potential drop across the resistor. This implies that Q equal to VL upon VR or Q equal to VC upon VR. So when we write VL upon VR, then in place of VL, we write I into XL. And in place of VR, we write I into R. So I will cancel out. So we will have Q equal to XL upon XL upon R, and XL can be written as omega R into L, where resonant frequency, because quality factor is always associated with resonant frequency. So omega L is the inductive reactance. So here for the resonance frequency, inductive reactance becomes equal to omega R into L divided by R. This is quality factor. Now if we use capacitor, voltage across capacitor and resistor, then quality factor equal to VC divided by VR. And in place of VC, we write here XC into I into XC and divided by I into R. So I will get cancelled out. Now we have XC divided by R. Now in place of XC, we put 1 upon omega C. So we get here 1 upon omega R into CR. So we see here quality factor depends inversely as capacitance and resistance. And here quality factor also depends inversely with the resistance. So if resistance increases, quality factor decreases. That is, sharpness of resonance will go on decreasing with increase in resistance. But one more thing, with increasing capacitance, quality factor will decrease. But with increase in inductance, quality factor will increase for the given resonance conditions. So this was the all about LCR circuit, and now looking at this, we have three curve, resonant curve. We have three resonant curve here given. One is more sharp curve here, you see. It is more sharp curve, and comparatively this is less sharp and this is negligibly sharp. So bandwidth increases, with increase in resistance, and sharpness will decrease. So as this is more sharp curve, so resistance R1 will be a smallest, and this is the comparatively less sharp, so R2 will be greater than R1, and this curve is least sharp, so R3 will be greatest of all the resistance R1 and R2. It's okay. Now we are going to discuss about the power in AC circuit across LCR circuit. So we discuss here power across LCR circuit. As we know that alternating EMF supplied by the AC source is given as A equal to E naught sin omega t. Say this is equation 1. And we have already calculated that phase difference between current and voltage across LCR circuit will be phi. Phi might be positive or negative depending on value of XL and XC. So here we assume that here phase difference is positive, indicating that current leads the voltage by a phase difference of phi, and hence instantaneous value of current will be represented as I equal to I naught sin omega t plus phi, because current differ by voltage by phase difference of plus phi. So instantaneous voltage is E naught sin omega t, instantaneous current equal to I naught sin omega t plus phi. So we have to calculate instantaneous power. So we know that product of voltage and current is equal to electrical power. So here instantaneous power, in order to calculate instantaneous power across LCR circuit, we multiply instantaneous voltage and instantaneous current together, and so we get here E naught into I naught sin omega t plus phi. Keeping this sin omega t as usual, and we expand this term as sin A plus B equal to sin A into cos B plus cos A into sin B. So we have expand this term and then multiply by this term sin omega t. So we get here sin square omega t cos phi plus cos omega t sin cos omega t into sin omega t into cos phi. So here we see, if we take the average value of this term, you will get 0, because average of sin omega t over full cycle is 0, average of cos omega t over full cycle is 0, because both the function is periodic. But average of sin square omega t will be half, and hence you will get the average instantaneous power. Average power will be obtained because this is expression for instantaneous power. If the instantaneous power is assumed to be constant for an infinitesimally small time dt, so when power is multiplied by time, then we get amount of work. Then work done is obtained as E naught I naught sine square omega t cos phi plus sine omega t cos omega t into cos phi into here dt, which has been left. So you must place here dt, and then each term inside the bracket uh, dt will be there, here also dt and here also. So work done over a complete cycle is obtained at 0 to t E naught I naught sine square omega t cos phi plus sine omega t cos phi into dt here we get. So after integration over a limit 0 to 0 to t, we will get that this term will vanish, will give the zero value. So only we will have value of this one, that is 1 by 2. So we will get this terms here, E naught I naught cos phi into t by 2. So we will get here average power. Power is equal to what? Work done divided by time. So this is the average work done over full cycle. So average power is just equal to average work done divided by time. So W by T, and hence this T will be cancelled out. So we will have average power E naught I naught upon 2 cos phi. And this 2 can be expressed as product of root 2 into root 2. So here we have placed E naught divided by root 2 and I naught divided by root 2 into cos phi. And E naught divided by root 2 is nothing but RMS value or virtual value of alternating EMF or alternating current. We say this one is as RMS. So remember, E naught divided by root 2 equal to ERMS and I naught divided by root 2 equal to IRMS or virtual value, and cos phi is called power factor because all the terms here remains constant. So power depends on value of phi, that is phase difference between current and voltage. So when phase difference between current and voltage becomes 90 degree or pi by 2 radian, then cos pi by 2 radian equal to 0, and in that case power becomes 0. Although current and voltage is non-zero, still we will have power 0. In such situation, we say that wattless current, because although current is there in the circuit but giving no power, so such situation is called wattless current. Wattless current is the situation when phase difference between current and voltage is pi by 2 radian or 90 degree. That situation is called wattless current. And you have already learned that across inductive circuit and across capacitive circuit, phase difference is pi by 2. Therefore, inductive circuit and capacitive circuit does not dissipate any power supplied to it. No power is consumed across inductive and capacitive circuit. So here cos phi is called power factor. And cos phi, if you look at the triangle here, yes, here in this triangle, you will obtain the cos equal to what? Cos equal to base upon hypotenuse. So base is VR and hypotenuse is equal to this one, E. And in place of VR, we can write here I into R. In place of E, we can write here I into Z. So ratio of I into R divided by I into Z. So I will be cancelled out and we will get here R by Z. So you see here R by Z. This is power factor. Power factor depends on impedance. So power factor is a variable because as we see that impedance is frequency dependent resistance. So as impedance increases, power factor decreases, and if power factor decreases, then power across the circuit will also decreases. Now let us check out when this term becomes 0, then value of cos phi becomes equal to 1. So at resonance situation, this term will get vanish. Omega L minus omega 1 upon omega C will vanish, and hence this term will vanish. Only square root under r square will be there, and r square will come out of the root, then r by r equal to 1. In that situation, power factor will be equal to 1. So at the resonance situation, power factor cos phi will be equal to 1. And this is the expression for average power. Average power is just equal to ERMS into IRMS into cos phi, where cos phi is called power factor. I think that time is